All right, let's dive right into this explainer. Today, we're unpacking something absolutely fascinating and, yeah, highly technical. We're looking at how to assess the safety of complex, unpredictable dynamical systems using probabilistic model checking. We're drawing directly from a brilliant paper by Lena Becker and Holger Hermans, which actually tackles a fundamental flaw in how engineers have traditionally analyzed the stability of these unpredictable systems. It's a real game changer.
To properly unpack this paradigm shift, we're going to follow a clear roadmap. 1. Modeling unpredictable dynamical systems. 2. The global stability trap. 3. Model checking with PCTL. 4. Defining new stability operators. And 5. The math behind the logic.
So, Section 1, Modeling Unpredictable Dynamical Systems, Grasping the Basics.
Now, what's really interesting about this mathematically is how we actually represent systems that experience abrupt, random changes. Think about drones suddenly hit by massive gusts of wind, or a power grid dealing with localized failures. How do we model that mathematically? Well, the answer is Markov Jump Linear Systems, or MJLS. And MJLS is honestly perfect for modeling real-world uncertainty. Imagine a lower limb exoskeleton helping someone walk. The basic physical movement is continuous, right? But what happens if the terrain suddenly changes, or a sensor just glitches out? This system has to immediately jump to a different mode of operation. In an MJLS, the continuous state, like the physical position of that exoskeleton, evolves in a linear way, but it's constantly subject to abrupt, probabilistic switches between different operational modes. And those random switches, they're governed by an underlying Markov chain.
To see exactly what this looks like under the hood, let's completely break down a three-mode Markov chain that governs an MJLS. Picture three circular nodes, each representing a distinct linear mode of the system. We'll label them 1, 2, and 3. Connecting these nodes are arrows, and these arrows represent the exact transition probabilities between the modes. For example, if you look at mode 1, you might see a looping arrow pointing right back to itself, indicating a 1 in 7 chance the system just stays in mode 1. But there's a 1 in 4 chance it jumps over to mode 2, and a 3 in 7 chance it jumps down to mode 3. Every single step in time, the system is literally rolling the dice based on these exact probabilities to determine its next dynamic mode. It's a constant, probabilistic dance.
Moving right along to Section 2, the global stability trap, why current methods fail.
Let's see how this unpredictability builds into a major problem when it comes to the overly conservative nature of how engineers currently evaluate stability. Traditionally, engineers check for mean stability or mean square stability. These are global guarantees. Global stability requires that all initial states converge to zero over time. So here's the crucial point. A system might actually be totally safe for all practical purposes, but it gets falsely flagged as unstable just because some theoretical, frankly impossible initial state mathematically diverges. State-specific stability, on the other hand, evaluates stability only for a specific, physically relevant subset of initial conditions. It's way more practical.
The source text hits the nail on the head here. It notes that instability might arise only for a small fraction of initial states that may not even be of practical relevance, such as physically impossible operating regions of a drone. I mean, think about it. If your drone can never physically reach an altitude of negative 50 feet, why should a mathematical divergence at negative 50 feet cause you to scrap the entire control system? It makes no sense. We need a way to check stability only for the states that actually matter.
Which brings us to Section 3, Model Checking with PCTL, a logical solution.
To fix this whole global stability trap, we turn to the realm of computer science and introduce Probabilistic Computation Tree Logic, or PCTL. PCTL natively reasons about specific sets of initial states. It acts as this incredibly powerful branching time objective framework. It lets us evaluate temporal properties for specific starting points. It can compute the probability of reaching certain safety sets. It handles step-bounded properties, meaning we can actually give the system a grace period to stabilize. And crucially, it safely embeds logical operators to tackle continuous states by labeling them using something called convex polytopes.
Now, what exactly is a convex polytope? Mathematically, it's a bounded, convex subset of a multidimensional space. Think of it like a multidimensional stop sign. Why are they chosen for this? Because operations like linear transformations and intersections perfectly preserve their exact structure. This means when we run our complex model checking algorithms, the math remains computationally manageable. It doesn't spiral out of control.
All right, Section 4, Defining New Stability Operators, Capturing the Moments.
Let's step into the true paradigm shift of this explainer, extending standard PCTL to capture the first and second moments of an MJLS.
The authors extend the logic by adding new moment-based operators. In the equations, you'll see E for expected value, that's the first moment, and V for uncentered variance, the second moment. By adding these specific operators, we're no longer just asking the binary question, does the system eventually reach zero? Instead, we're asking a much smarter question. Does its average behavior eventually settle within our acceptable safe zone as defined by a polytope?
To actually calculate this long-term behavior, the authors use Cesaro limits. This means they look at the limit of time-averaged values. And this brilliantly illustrates exactly why classical stability is so flawed. A standard pointwise limit will fail and label a system unstable if the system continuously oscillates. But by taking the time-averaged Cesaro limit, the logic smoothly accommodates that oscillatory behavior, giving us a much more accurate picture of practical stability.
Finally, Section 5, the math behind the logic, visualizing the proof.
Now we arrive at the most visually compelling part of our explainer, where we thoroughly explain the mathematical geometry of these satisfaction sets in practice. Imagine a mapped-out two-dimensional continuous state space. Within this space, we have two distinct convex polytopes. First, there's a smaller purple geometric area, labeled pi. This is our target expected value zone. Ultimately, we want the long-run expected state of our system to land right inside that purple shape. Surrounding it, there's a larger teal geometric area, labeled lambda. This is our safe bounding zone. This entire setup allows us to create what's known as a reach-avoid scenario. Basically, we desperately want the system to reach the purple target while strictly avoiding any states outside the teal safe zone along the way.
So how do we know which initial conditions actually pull this off? Well, let's visualize the exact continuous initial states that satisfy our formulas. Picture colored lines plotting the states, blue for mode 1, red for mode 2, and yellow for mode 3. In the first scenario, visualizing the basic long-term expected value, we see the specific cluster of initial states across all three modes that successfully find convergence inside our purple target area over infinite time. But it gets even more complex. Imagine a second scenario, finding the initial states that satisfy reaching the target area in exactly 5 steps, while maintaining at least a 30% probability of staying entirely within the teal safe zone during that grace period. When you map that, you notice the valid initial states shift and drastically constrain. Only a highly specific, restricted subset of initial conditions can pass this rigorous, step-bounded safety check across the respective operational modes. It's incredibly precise.
Under the hood, the linear algebra engine driving all of this relies on a very specific sequence. First, the expected values are propagated using a massive block diagonal matrix called matrix B. Next, the algorithm computes eigenvalues to check for baseline mean stability. Now, if the matrix is diagonalizable, it cleverly uses linear combinations of eigenvectors to find the stable limits. But if it is not diagonalizable, the algorithm has to use Jordan normal form blocks to systematically isolate and remove mathematically diverging sequences using symbolic tracking.
But there's a fascinating and pretty hard computational barrier here. To find those eigenvalues, you have to find the roots of a polynomial. However, as dictated by the Abel-Ruftini theorem, there is literally no general closed-form algebraic solution for finding the roots of polynomials of a degree greater than 4. There's just no way around it. This means for even slightly complex multidimensional systems, exact analytical computation hits a brick wall, and we absolutely must rely on numerical approximations to map these spaces.
Which leaves us with a pretty provocative final thought. This paper successfully solves state-specific stability for MJLSs by leveraging these limits and approximations. But if checking unbounded reachability for a basic 4-dimensional deterministic linear dynamical system remains a notoriously unsolved mathematical puzzle tied to the famous Scullin problem, what other profound mysteries remain entirely hidden in the uncountable depths of general Markov processes? It's a wildly tantalizing frontier. Well, that's all for this explainer. Keep asking questions and keep learning.